They told us 3I Atlas was just cosmic debris, another interstellar rock tumbling through our solar system, interesting only to astronomers with too much time and too many telescopes. They were catastrophically wrong. Because 3 hours before this object reached its closest point to Earth, sensors across Russia registered something that shouldn't exist. A single electromagnetic frequency, 25 Hertz, perfectly stable, impossibly precise. The exact signature detected before Japan's earthquake 11 days earlier. Now here's where it gets uncomfortable. Natural systems don't schedule events. They don't use countdown timers. They don't probe before arrival. But something did. Stay until the end. Because the timing of this signal suggests Earth just received a message we're not ready for. You'll want to keep watching as the truth about 3I Atlas unfolds. Hit subscribe and follow along, because what happens in the coming hours might answer questions we didn't know we should be asking. The universe doesn't give up its secrets easily, but together, we're about to see if this signal was a goodbye or something far more unsettling. They said it was nothing. Just another rock from beyond our solar system, tumbling through the void like countless others we'll never see. 3I Atlas, they called it. Interstellar Object Number 3. The third confirmed visitor from another star system, here to swing past Earth and disappear back into the cosmic dark. Scientists tracked it. Amateurs photographed it. News outlets gave it a paragraph, maybe two, and then everyone moved on. Except someone forgot to tell the censors. At 0240 Coordinated Universal Time on December 19th, 2025, monitoring stations across Russia registered something that shouldn't exist. Not in theory, not in practice, not according to any natural process we understand. A single electromagnetic spike, narrow as a laser cut, centered precisely at 25 Hertz. No drift, no wobble, no harmonic bleed into neighboring frequencies. Just one clean, surgical pulse in the extremely low frequency range, the kind of signal that makes geophysicists sit up straight and check their instruments twice. You need to understand what makes this strange. Earth produces electromagnetic noise constantly. Lightning strikes generate broadband static that splashes across the spectrum like paint thrown at a wall. Solar storms send charged particles cascading through our magnetosphere, creating waves that shimmer and pulse across multiple frequencies simultaneously. Even human activity, all our power grids and radio towers and electrical infrastructure, bleeds energy into the environment in messy, chaotic patterns. Nature is noisy. Nature is sloppy. Nature doesn't do precision. This signal was precise. The sensors that caught it weren't amateur equipment. These were vertical electric field measurement stations, purpose-built ELF antennas designed specifically to filter out environmental interference. They reject lightning signatures automatically. They compensate for weather variations. They're calibrated to ignore the constant electromagnetic chatter of human civilization. What they're built to detect are anomalies in the Schumann resonances, those natural electromagnetic frequencies that oscillate in the cavity between Earth's surface and the ionosphere. And Schumann activity, when you look at it on a spectrograph, appears as broad, fuzzy bands of energy spread across multiple frequencies like a musical chord played on an out-of-tune piano. This wasn't that. This was a single note, held perfectly steady, appearing and vanishing like someone had flipped a switch. The first response was predictable. Someone checked for lightning strikes in the region. Nothing. Someone else pulled up geomagnetic activity reports, looking for solar storm indicators. Calm conditions. Quiet sun. No coronal mass ejections, no particle bursts. Nothing that could explain a localized electromagnetic event. Then came the uncomfortable questions. Could it be military? Some classified test of submarine communication systems? Except submarine ELF transmitters produce continuous wave signals, not brief pulses. and they don't appear at exactly 25 Hertz, a frequency with no tactical communication value whatsoever. Human activity was ruled out. Natural causes were ruled out. Equipment malfunction was ruled out after cross-referencing data from multiple independent monitoring stations, which left exactly one thing on the table: the timing. Because 0240 UTC wasn't just any moment. It was the exact window when 3I Atlas made its closest approach to Earth, not days before its flyby, not hours after it had passed. Inside the same observational window, when this interstellar object, this visitor from another star system, came within its minimum distance from our planet. You could call that coincidence. You could argue that random events cluster sometimes, that the universe doesn't care about human pattern recognition, that we're evolved to see faces in clouds and meaning in static. But coincidence doesn't explain precision. Behind the scenes, away from press releases and public statements, geophysicists began having very quiet conversations. The kind of conversations where everyone speaks carefully, where words like anomaly and requires further study get used instead of anything more direct. There was hesitation, institutional hesitation. The kind that comes from knowing how badly a false alarm can damage credibility, how quickly a reputation can collapse under the weight of extraordinary claims that turn out to be ordinary mistakes. So they waited. They reviewed data. They ran checks and cross-checks. They looked for any explanation, any mundane reason this signal could exist without meaning anything unusual. And they found nothing. Not alarming enough to trigger emergency protocols. Not ignorable enough to dismiss as background noise. Too clean to be natural. Too isolated to be human-made. Too precisely timed to be comfortable. One researcher, speaking off the record, put it this way: if this were random, it wouldn't be this precise. And that's where we are. No claims of alien contact. No declarations of discovery. Just a signal that behaves unlike any natural electromagnetic phenomenon we've documented, appearing at the exact moment an object from interstellar space passed closest to our world. The data is verified. The timing is confirmed. The signal characteristics are unlike standard geophysical activity. Everything else is interpretation, and interpretation is where science gets dangerous, where careers end and ridicule begins. But here's what nobody's saying out loud yet. What nobody wants to put in a formal report or attach their name to until they're absolutely certain. This signal, this 25 Hertz pulse that appeared during the 3I Atlas flyby, it's not the first time we've seen it. Not even close. And what happened after the last time we detected this exact frequency signature is something that keeps seismologists awake at night. Something that changed how monitoring networks operate. Something that made this new detection feel less like a curiosity and more like a countdown. We need to talk about Japan. December 8th, 2025. Magnitude 6.8. The earthquake struck off Japan's coast with enough force to rattle buildings in Tokyo and send coastal communities scrambling for higher ground. Standard tectonic activity for one of the most seismically active regions on Earth. Except for one detail that wasn't standard at all. One detail that got buried in the technical appendices of monitoring reports and never made it to mainstream coverage. Days before the quake hit, sensors detected anomalous ELSIF behavior. Same narrow frequency window, roughly 24 to 26 Hertz. Same surgical precision, same lack of harmonic spread, same characteristics that separate engineered signals from natural phenomena. And then the Earth moved. Now, before you jump to conclusions, understand what scientists actually agree on. Electromagnetic anomalies are not accepted earthquake predictors. They're not part of any operational early warning system. No seismologist worth their credentials will tell you that detecting an ELF spike means a quake is coming. The relationship between electromagnetic activity and seismic events is studied, yes. Discussed in academic papers, yes. But treated as predictive? Absolutely not. The data is too inconsistent. The mechanisms are too poorly understood. The risk of false positives is too high. But that doesn't mean these signals are ignored. Crustal stress does weird things to the electromagnetic environment. When rock compresses under tectonic forces, when pressure builds along fault lines, strange electrical effects can occur. Piezoelectric responses in quartz-bearing rock. Charge. Redistribution in the lithosphere. Ionospheric coupling that creates detectable electromagnetic signatures at the surface. It's not mystical. It's physics. Poorly understood physics. Controversial physics. But physics nonetheless. And 25 Hertz keeps appearing in the literature. Not always. Not reliably. But often enough that dismissing it entirely requires ignoring a growing body of observations. Here's what makes the Japan event different. These narrow-band LF spikes are rare. Genuinely rare. Months can pass without any comparable detection. Background Schumann activity is constant, sure, but clean, isolated, narrow-band signals at specific frequencies? Those are outliers. Anomalies within anomalies. The kind of thing that happens maybe once or twice a year across all global monitoring networks combined, if you're being generous with your definitions. So, when one appears days before a significant earthquake, it gets flagged. Quietly. Internally. Not as proof of causation, but as correlation worth documenting. And when a second comparable event appears less than 2 weeks later, synchronized with an interstellar object's closest approach to Earth, that's when dismissal becomes harder than acknowledgement. Monitoring networks changed after Japan. Nothing dramatic, nothing announced publicly, but thresholds got recalibrated. Attention shifted toward narrow band signals. Protocols were updated to flag similar detections faster, to cross-reference them more thoroughly, to treat them as potentially significant, rather than automatically discarding them as instrument artifacts. You don't make those changes unless something made you uncomfortable. Unless correlation without mechanism started feeling less like coincidence and more like pattern. And patterns are what terrify scientists, because patterns demand explanation. Patterns require mechanisms. Patterns can't be dismissed with a shrug and a reminder that sometimes unlikely things happen. One anomaly preceding a major earthquake is noise. Random chance. The universe being weird, but two anomalies, both at the same frequency, both isolated and precise, both followed by or synchronized with significant events, that's different. That's repetition. That's when institutional discomfort turns into institutional attention. Nobody is claiming the signal caused the Japan earthquake. Let's be absolutely clear about that. Correlation is not causation, and any scientist who suggests they can predict earthquakes based on electromagnetic signatures is either lying or dangerously overconfident. The mechanisms aren't understood well enough. The data isn't consistent enough. The physics isn't solved. But here's what is being quietly acknowledged in research circles. If these signals are associated with crustal stress, if they represent some kind of electromagnetic fingerprint of tectonic systems under extreme pressure, then detecting them matters. Not for prediction, for observation. Think of it like hearing ice crack before it breaks. You're not causing the crack by hearing it. You're not predicting exactly when the break will happen. But you know something is under stress. You know the system is loaded. You know conditions are primed for failure. That's all these signals might represent. Stress indicators, system diagnostics, evidence that something deep in Earth's geology is approaching a threshold. But that interpretation only works if the signals are coming from Earth. If they're generated internally by crustal stress, by piezoelectric effects, by charge redistribution in compressed rock, then fine. Unusual, poorly understood, but ultimately geological. A planet talking to itself in frequencies we're only beginning to hear. The 3i Atlas signal throws that interpretation into chaos. Because if an identical electromagnetic signature appears during an interstellar object's flyby, synchronized with its closest approach, then suddenly you're not looking at internal Earth processes anymore. You're looking at correlation across systems. You're looking at an interstellar object and Earth's electromagnetic environment responding simultaneously. And that raises questions that make the Japan precedent feel less like geology and more like something we don't have vocabulary for yet. 1 anomaly is noise. 2 is a pattern. 3 is a warning. We're at 2. The question is whether we're waiting for 3, or whether 3 already happened and we're just not calling it that yet. Here's the detail they buried in the technical reports. The detail that doesn't make sense if you're thinking about passive physics, about gravitational effects or magnetic field interactions, or any of the conventional ways celestial objects influence each other from a distance. The signal didn't occur at closest approach. It occurred 3 hours and 20 minutes before closest approach. Let that sink in for a moment. If you're thinking about tidal effects, about gravitational stress, about an object's mass influencing Earth's crust or electromagnetic environment through conventional forces, those effects should peak when the object is nearest. Maximum proximity equals maximum interaction. That's basic physics. The moon doesn't create its strongest tidal pull 3 hours before it passes overhead. Solar radiation doesn't peak before the sun rises. Gravitational interactions don't schedule themselves, but this signal did. 3 hours and 20 minutes is too long to be measurement error. Too long to be explained by propagation delays in Earth's electromagnetic environment. Too long to dismiss as timing coincidence. It's a specific offset, a precise lead time that suggests something other than passive interaction. And when you start thinking about active processes, about systems that operate on schedules rather than responding to proximity, the comparisons that come to mind aren't natural anymore. Sonar operates on lead time. You send a ping before you need the return data. Radar illumination happens before target acquisition. Probing systems, diagnostic systems, measurement systems, all of them use advanced signals to gather data before primary interaction. You don't wait until you're directly overhead to test a system. You probe first. You measure first. You send your signal and wait for the response, analyzing what comes back before committing to whatever comes next. That's engineered behavior. That's designed interaction. And the moment you start using those words, the moment you start comparing this event to active systems rather than passive physics, you've crossed a line that most scientists refuse to approach publicly. Could this still be coincidence? Absolutely. Could there be some natural explanation we haven't thought of yet? Some electromagnetic propagation effect that creates precisely timed offsets between cause and detection? Maybe. Nature is stranger than we imagine, and our understanding of how interstellar objects interact with planetary electromagnetic environments is functionally non-existent, because we've only detected 3 such objects ever, and none of them behave like this. But coincidence doesn't explain why that specific offset. If the signal were random, if it were unrelated to the flyby, why would it appear exactly 3 hours and 20 minutes before closest approach? Why not 6 hours? Why not 30 minutes? Why not simultaneous? Random events don't cluster around specific intervals. They scatter. They spread. They appear when they appear without regard for schedules or countdowns. This appeared on a schedule. Some researchers, speaking carefully and off the record, have started using terms like resonant priming. The idea being that instead of applying force directly, instead of pushing or pulling or disturbing Earth's systems through conventional electromagnetic or gravitational interaction, something could be establishing resonance first. Setting up conditions, tuning systems to specific frequencies before the main event. Think of it like preheating an oven. You're not cooking yet, You're preparing the environment. You're establishing the conditions that will matter when actual interaction begins. Is that what happened? Nobody knows. Nobody can prove it. But the timing offset is real, documented, verified across multiple monitoring stations. The signal appeared 3 hours and 20 minutes before 3i Atlas reached its closest point to Earth. That's not interpretation. That's measurement. What it means is where interpretation begins and consensus ends. The uncomfortable questions start multiplying. If this was measurement rather than impact, if something was testing Earth's electromagnetic response rather than affecting it directly, what was being measured? What data would you gather from a 25 Hertz pulse sent into a planetary electromagnetic environment? What would the return signal tell you about crustal stress, about tectonic stability, about fault lines loaded? With centuries of accumulated strain? Everything. A resonance test at 25 Hertz would tell you everything about where Earth's crust is most vulnerable, where pressure has built beyond equilibrium, where systems are primed for failure. It's the geological equivalent of tapping on a frozen lake to find thin ice. You're not breaking the ice by tapping. You're measuring its response. You're identifying weak points. You're mapping instability through acoustic feedback. And if you're mapping instability, if you're conducting measurements rather than applying force, then proximity becomes irrelevant. You don't need to be close to send a signal. You don't need to touch something to test it. You just need the right frequency, the right timing, and the willingness to wait for a response. Natural systems don't use lead times. Natural systems don't schedule events. Natural systems respond to immediate conditions, to forces present in the moment, to stimuli that exist right now. Delayed effects exist in nature. Sure, sound travels slower than light. Seismic waves take time to propagate. But those are propagation delays, not operational schedules. The cause still happens first. The effect follows after. This signal appeared before the cause should have existed, before closest approach, before maximum interaction, before any conventional physical model would predict electromagnetic disturbance from a passing object, which means either our physical models are incomplete or something was operating on a schedule that natural physics doesn't follow. Why interact before arrival? What purpose does a 3-hour, 20-minute lead time serve unless you're gathering data, unless you're testing systems, unless you're measuring response before committing to something larger? That's the question nobody wants to ask out loud, because asking it implies intention. It implies design. It implies that 3i Atlas wasn't just passing through. It was doing something, testing something, measuring something, or maybe preparing something. Earth is not isolated. We think of our planet as a discrete object, a solid sphere of rock and metal floating through space, separated from the universe by vacuum and distance. But that's not how electromagnetic systems work. Earth exists inside a complex, interconnected web of magnetic fields, charged particles, and electromagnetic resonances that extend far beyond our atmosphere. We're part of a system, the Sun-Earth-Space environment. And in systems, distant events can trigger local responses without ever making physical contact. The Earth ionosphere cavity is real. It's the gap between our planet's surface and the lower edge of the ionosphere. That layer of charged particles about 60 kilometers up where solar radiation strips electrons from atmospheric molecules. This cavity acts like a resonant chamber. Electromagnetic waves bounce between the ground and the ionosphere, creating standing waves at specific frequencies. The Schumann resonances, usually around 7.8 Hertz for the fundamental frequency, with harmonics extending upward. These are natural, continuous, the electromagnetic heartbeat of the planet. But resonant systems have peculiar properties. They respond disproportionately to inputs at or near their resonant frequencies. Push a child on a swing at random intervals, and nothing happens. Push at the swing's natural frequency, and amplitude builds with minimal effort. The same principle applies to planetary-scale electromagnetic systems. The right frequency, applied at the right moment, can create effects far larger than the energy input would suggest. 25 Hertz sits in an interesting place. It's not a primary Schumann frequency, but it's close to documented harmonics. More importantly, it appears repeatedly in fringe research and some legitimate studies examining electromagnetic precursors to seismic events. Why that frequency? Nobody knows for certain. But if you were testing a system, if you were probing to see how a planet responds electromagnetically, you wouldn't choose a random frequency. You'd choose one that matters, one that couples to systems you want to observe. The lithosphere, that rigid outer layer of Earth's crust, is sensitive in ways we're still discovering. Stress-loaded fault lines, sections of crust compressed by tectonic forces and locked in place by friction, exist in states of precarious equilibrium. They're primed systems, spring-loaded. All they need is the right perturbation, the right trigger, and centuries of accumulated stress releases in seconds. Earthquakes don't require massive external forces to initiate. They require timing. They require the right push at the right moment in the right place. There's research, controversial and far from consensus, examining whether electromagnetic fields can influence seismicity. Not cause earthquakes, that's too strong, but trigger them in systems already loaded with stress. The mechanism involves piezoelectric effects in rock, charge redistribution along fault boundaries, possible coupling between electromagnetic fields and the electrokinetic properties of fluid-filled fractures. It's studied, it's published, it's debated, and it's nowhere near accepted as mainstream understanding. But let's use an analogy. Imagine a guitar string under tension. You don't need to hit it with a hammer to make it vibrate. You don't need massive force. You just need to pluck it at the right point with the right timing. The string already contains potential energy from tension. Your input doesn't create that energy. It just converts potential into kinetic. It releases what was already there, waiting. Earth's crust in tectonically active regions is a guitar string under tension. Fault lines are loaded. Stress is accumulated. Energy is stored. All that's missing is the pluck. And if electromagnetic fields can provide that pluck, if the right frequency applied at the right moment can redistribute charge or alter friction coefficients or modify fluid pressure in ways that tip a system from stable to unstable, then you don't need to hit the planet. You don't need mass or momentum or kinetic impact. You just need to tune it. This is speculation. Let's be clear about that. This is not mainstream consensus. Most geophysicists would consider electromagnetic triggering mechanisms to be fringe at best, pseudoscience at worst. The data is inconsistent. The mechanisms are poorly understood. The correlations are weak. But dismissing it entirely requires ignoring published research, documented observations, and the growing body of evidence that Earth's electromagnetic and seismic systems are more coupled than classical models suggest. If 3i Atlas sent a 25 Hertz pulse into Earth's electromagnetic environment 3 hours before closest approach, and if that pulse coupled to crustal stress systems already primed for failure, then proximity becomes irrelevant. Distance doesn't matter. Physical contact doesn't matter. All that matters is frequency, timing, and whether the receiving system is sensitive enough to respond. And here's what makes this possibility genuinely unsettling. If you can affect a system remotely through resonance, if you can trigger responses without direct contact, then traditional ideas about safety distance collapse. You don't need to be close. You don't need to threaten collision or gravitational disruption. You just need to understand the system well enough to know which frequency matters, which timing works, which systems are vulnerable. A probe from interstellar space, if it were designed rather than natural, wouldn't need weapons. It wouldn't need mass drivers or kinetic impactors or any conventional means of interaction. It would just need sensors capable of detecting electromagnetic signatures from a distance. Instruments able to measure crustal stress through electromagnetic response, and the ability to send a signal at the right frequency to test whether the planet responds the way models predict. You don't smash the guitar string, you pluck it. And if it's already under tension, if it's already primed, it does the rest itself. That's the possibility nobody wants to say out loud. Not because it's proven, not because it's likely, but because if it's possible, then the question stops being whether 3i Atlas was dangerous and becomes whether it was curious, whether it was measuring, whether it was testing, whether it's still watching to see what happens next. Let's ask the question everyone's thinking, but nobody wants to speak. Was this intentional? Was that signal deliberate, designed, transmitted by something with purpose, rather than generated by accident or natural process? Because if we're being honest, if we strip away institutional caution and professional risk avoidance, the characteristics of this event don't look accidental. 25 Hertz is terrible for communication. Genuinely terrible. Low frequency means low bandwidth. You can't transmit complex information efficiently at extremely low frequencies. It's like trying to send a novel via telegraph when you have high-speed internet available. Any civilization capable of interstellar travel would have access to vastly superior communication methods. Radio, optical, maybe technologies we haven't even conceived. So if this was meant as a message, as first contact, as "Hello universe, we come in peace," it failed spectacularly at being informative. But flip the question. What if communication wasn't the point? What if this was system testing instead? Suddenly, 25 Hertz makes perfect sense. High Q factor. That's the technical term. It means a signal that's spectrally pure, energetically efficient, focused entirely within a narrow frequency band with minimal waste. If you're testing whether a planetary electromagnetic environment responds to specific frequencies, you don't want broad-spectrum noise. You want a clean signal. One frequency, maximum precision, minimal ambiguity about what you sent versus what came back. This signal had characteristics associated with engineered systems: frequency stability, spectral purity, precise timing. Those aren't impossible in nature, but they're unusual. They're the signatures of controlled processes rather than random ones. Lightning doesn't produce narrow band emissions. Solar storms don't generate single frequency spikes. Crustal stress might, maybe under specific circumstances, we don't fully understand. But even then, the timing becomes problematic. The correlation with 3i Atlas's approach becomes harder to dismiss. And then there's the silence. No follow-up signal. No repetition. No obvious attempt to establish sustained communication or demonstrate pattern. Just one pulse and then nothing. Radio silence. Which could mean malfunction, could mean natural origin, could mean we're desperately seeking pattern in randomness. Or it could mean something else entirely. It could mean the signal accomplished its purpose. It could mean the test was completed. It could mean whatever needed measuring got measured and continuation was unnecessary. Silence can be a signal too. Think about how you'd test an unknown system if you were concerned about revealing your presence or capabilities too early. You'd send a minimal probe, one pulse, just enough to gauge response without triggering alarm. You'd measure what came back, analyze the data, and then make decisions based on what you learned. You wouldn't announce yourself. You wouldn't declare intentions. You'd gather information first. Intelligence, whether human or otherwise, tends to prefer observation before engagement. SETI, the search for extraterrestrial intelligence, operates under constraints most people don't appreciate. Extraordinary claims require extraordinary evidence. That's not just a philosophical position. It's a survival mechanism for scientific credibility. Claim alien contact without bulletproof evidence, and your career ends. Your institution loses funding. Your research becomes punchline material. So SETI researchers are cautious to the point of paralysis when it comes to potential signals. They'll study. They'll analyze. They'll publish technical papers examining anomalous data. But declare contact? That requires certainty beyond any reasonable doubt. This signal doesn't meet that threshold. Not yet. Maybe not ever. There are too many unknowns. Too many possible natural explanations, however unlikely. Too much room for error or misinterpretation. So institutional response is silence. Not because the signal is unimportant, because the risk of false alarm outweighs the immediate value of public declaration. Better to study quietly, to verify thoroughly, to build consensus slowly, than to announce prematurely and face credibility collapse. But silence creates its own problems. It leaves room for speculation, for conspiracy, for narratives about data being suppressed, or access being restricted, or governments knowing more than they're telling. Some of that is paranoia. Some of it might be legitimate caution. Restricted access to certain monitoring data isn't necessarily sinister. It's often practical. Sensor networks maintained by military or government institutions have dual-use applications. They monitor electromagnetic environments for both scientific and defense purposes. Sharing that data completely and publicly could reveal capabilities or sensor placements that nations prefer to keep confidential. So we get partial disclosure, technical papers with redacted locations, monitoring reports that confirm signals without providing complete instrumentation details. Enough information to verify something unusual happened, not enough to independently analyze every aspect. Is that suppression? Is that caution? Is that standard operational security? Probably a mixture of all three, depending on who controls which data and what institutional priorities drive access decisions. Here's what remains unverified. No confirmation of artificial origin, no proof of intelligence, no decoded message or demonstrated intent. Just a signal with characteristics that don't fit comfortably into natural categories, appearing at a moment correlated with an interstellar object's approach. Everything else is inference, interpretation, speculation built on incomplete data, and professional discomfort with the implications. But speculation serves a purpose. It asks questions consensus won't touch yet. It explores possibilities that need examining even if they prove wrong. And the possibility that needs examining here, the one everyone's dancing around without stating directly, is this. Intelligence doesn't announce itself. Not immediately. Not obviously. Intelligence probes first. It tests boundaries. It measures responses. It gathers data before revealing presence or purpose. If 3i Atlas carried instrumentation, if it was designed rather than natural, its purpose might not be communication. It might be reconnaissance, measurement, cataloging which systems respond to which frequencies, which planets show electromagnetic signatures of tectonic stress, which worlds might be vulnerable to resonant triggering. You wouldn't announce that purpose. You'd just do it. Send your probes. Gather your data. Move on to the next system. And if that's what happened, if Earth just got scanned by an interstellar measurement system, then the real question isn't whether the signal was intelligent. It's what happens when the data gets analyzed. What conclusions get drawn? What follows reconnaissance? Because intelligence that probes doesn't stop at observation. It acts on information. It makes decisions based on what it learns. We might have just been tested, and we might not know the results until something else happens, until the next signal, until the next event, until whatever was set in motion by that 25 Hertz pulse 3 hours before closest approach reaches its conclusion. This isn't happening in isolation. While everyone focuses on 3I Atlas and electromagnetic anomalies, December 2025 has been quietly unusual across multiple scientific domains. Pattern recognition works better when you zoom out, when you stop looking at individual events and start noticing what they collectively suggest about changing conditions in our observation capabilities and cosmic awareness. AI-assisted telescope anomaly detection went operational at several major observatories this month. Sounds boring. Sounds like routine technological upgrade. It's not. Machine learning algorithms trained to identify non-Gaussian signals, statistical outliers that don't fit standard noise distributions, are now scanning astronomical data in real time. They're finding things human observers miss. Not because humans are incompetent, but because human attention has limits, and machine pattern recognition doesn't fatigue. These systems flag anomalies that would previously have been averaged out, smoothed over, dismissed as instrument artifacts. We're seeing the invisible. That's what improved instrumentation does. It doesn't change reality. It changes perception. And when perception shifts, when you suddenly detect signals you couldn't see before, it creates the illusion that phenomena are increasing in frequency. They're not. You're just noticing them now. Like upgrading from standard definition to high resolution. The image was always there. You just couldn't resolve the details. Consider what this means practically. Astronomical surveys generate terabytes of data every night. Human astronomers can't review all of it. They couldn't even when data volumes were smaller. So protocols got established. Thresholds got set. Anything below certain brightness levels gets ignored. Anything that doesn't repeat gets filtered. Anything that looks like known instrument. Artifacts gets discarded automatically. Those filters are necessary. They prevent drowning in noise. But they also guarantee that unusual events, one-time occurrences, subtle anomalies that don't fit expected patterns, get lost. Machine learning changes that calculation. AI doesn't get tired. It doesn't get bored. It doesn't dismiss anomalies because they're inconvenient or because investigating them would delay other work. It flags everything that deviates from trained expectations. And when you start catching everything, instead of filtering most things, the volume of detected anomalies increases dramatically. Not because anomalies are increasing, because detection is improving. That's the invisible becoming visible. That's resolution improvement, revealing complexity that was always present but unobservable. And it's happening simultaneously across multiple domains of scientific observation. Earth-space coupling research is exploding. Not literally, thankfully, but in terms of publication volume and institutional interest. The idea that electromagnetic, gravitational, and particle interactions between Earth and its space environment are more complex and consequential than classical models suggest is gaining traction. Studies examining how solar wind variations affect atmospheric chemistry. Research into magnetospheric resonances coupling to ionospheric dynamics. Papers exploring whether cosmic ray flux influences cloud formation, which influences climate, which influences just about everything. These aren't fringe topics anymore. This is mainstream geophysics and space weather research, and the cumulative picture emerging is uncomfortable. Earth is more sensitive to external influences than we assumed, more responsive, more coupled to cosmic conditions. Small perturbations in the space environment can cascade through multiple atmospheric and geological systems in ways we're only beginning to map. The implications extend beyond academic curiosity. If solar wind variations affect atmospheric chemistry, then space weather isn't just about satellite disruption and power grid vulnerability. It's about air quality. It's about ozone layer dynamics. It's about chemical processes that influence everything from agriculture to human health. If magnetospheric resonances couple to ionospheric dynamics, then electromagnetic conditions in space directly influence electromagnetic conditions at Earth's surface. And if cosmic ray flux influences cloud formation, then the galaxy itself participates in Earth's climate system. That last one particularly bothers climatologists. Climate models are complex enough already. They account for ocean currents, atmospheric circulation, greenhouse gas concentrations, ice sheet dynamics, vegetation feedback loops, and dozens of other interacting variables. Adding cosmic ray flux as another input, acknowledging that galactic conditions influence cloud formation, which influences albedo, which influences temperature, which influences everything else, means climate isn't just a planetary system, it's a cosmic system. Earth's climate responds to conditions light years away. Quantum sensors are contributing to this shift. These devices, which exploit quantum mechanical properties to achieve measurement precision impossible with classical instruments, can detect magnetic field variations at femtotesla scales. That's quadrillionths of a Tesla. For context, Earth's magnetic field is about 50 microtesla. Quantum sensors can detect changes a billion times smaller than that, which means subtle electromagnetic phenomena that were previously invisible are now detectable, measurable, analyzable. Think about that precision for a moment. A billion times more sensitive than standard magnetometers. That's not incremental improvement. That's revolutionary capability. And revolutionary capability reveals revolutionary complexity. Electromagnetic fields that seemed constant now show variation. Signals that seemed absent now appear clear. Correlations that seemed impossible now become measurable. What happens when multiple domains of observation capability improve simultaneously? When astronomical detection gets sharper, when electromagnetic monitoring becomes more sensitive, when quantum measurement pushes precision to previously impossible limits, you start seeing correlations you couldn't detect before. Patterns emerge. Not because the universe changed, but because your resolution improved enough to notice what was always there. And this is where things get genuinely strange. When you combine improved astronomical detection with enhanced electromagnetic monitoring with quantum precision measurements of Earth's magnetic environment, you create the conditions for discovering connections between phenomena we previously thought were unrelated. Interstellar objects and geophysical events, space weather and tectonic activity, cosmic conditions and terrestrial responses. Are those connections real? Are they causal? Or are they correlation artifacts created by increased observation density? That's the question haunting every researcher working at the intersection of these fields. Because if the connections are real, if Earth does respond to cosmic influences in measurable ways, then our models are incomplete. Our understanding of planetary dynamics is missing critical components. And events we've always attributed to purely internal processes might have external triggers we've been blind to until now. Statistical correlation increases with observation density. That's mathematics, not physics. The more data points you collect, the more correlations you'll find, including spurious ones. Ice cream sales correlate with drowning deaths because both increase in summer. Correlation without causation. Pattern without mechanism. And when you dramatically increase measurement sensitivity across multiple domains simultaneously, you create ideal conditions for finding correlations that mean nothing, except some of these correlations are persistent. They repeat across multiple observation cycles. They appear in independent datasets from different monitoring networks. They show up in historical data when reanalyzed with modern techniques. That persistence suggests something beyond statistical artifact. It suggests actual relationships between phenomena we didn't think were connected. 3I Atlas is the first interstellar object detected with modern quantum sensors operational, with AI anomaly detection online, with global electromagnetic monitoring networks operating at current sensitivity levels. We've observed two previous interstellar visitors, Oumuamua in 2017 2I/Borisov in 2019. Neither produced anything like this electromagnetic signature. But our detection capabilities in 2017 were fundamentally different than today. Sensors have improved, networks have expanded, analysis methods have evolved. So did Oumuamua produce similar signals we couldn't detect? Did 2I/Borisov interact electromagnetically with Earth in ways our instruments weren't sensitive enough to notice? Or is 3I Atlas genuinely different, genuinely unusual, genuinely doing something the previous visitors didn't? We can't answer that. We don't have the data. We can't retroactively improve observations from 8 years ago. Oumuamua was strange enough on its own. Its elongated shape, its tumbling rotation, its non-gravitational acceleration that suggested outgassing, but showed no cometary tail. Scientists debated whether it was a comet, an asteroid, or something else entirely. Some researchers, carefully and controversially, suggested it might be artificial, a light sail, a probe, something designed rather than natural. Those suggestions got dismissed as speculation, but they never got definitively disproven either. We just didn't have enough data. And now 3I Atlas appears with an electromagnetic signature we can detect, with timing we can measure, with characteristics that don't fit natural explanations comfortably. Is that because it's genuinely different, or because we're finally sensitive enough to see what interstellar objects actually do when they pass through our neighborhood? Which means we're operating in fundamental uncertainty. Every new capability reveals new phenomena. Every sensitivity improvement shows previously invisible signals, and we can't distinguish between "this is new" and "we can finally see this." That's humanity's blind spot. We assume what we observe now is complete. We build theories based on current data. We construct models from available measurements. And then instruments improve, and suddenly there are phenomena we couldn't see before, correlations we couldn't detect, patterns that force model revisions. The history of science is filled with examples. Microscopes revealed bacteria and cells. Telescopes revealed moons and galaxies. Particle accelerators revealed quarks and bosons. Each instrument improvement showed that reality was more complex than previous observations suggested. We weren't discovering new physics. We were finally observing physics that existed all along, but remained invisible to cruder instruments. This might be another such moment. The transition from classical to quantum precision electromagnetic monitoring. From human to AI-assisted astronomical observation. From isolated measurements to integrated multi-domain analysis. We're crossing thresholds of observational capability that reveal complexity we couldn't access before. The universe hasn't changed. Our resolution has. But resolution improvements have consequences. They reveal complexity we didn't know existed. They show connections we couldn't measure. They force questions about whether phenomena we've studied for centuries are complete, or whether we've been observing shadows and calling them reality. Plato's cave allegory applies. We've been watching shadows on the wall, interpreting them as complete reality, building models that explain shadow behavior. And now we're turning around, seeing the objects casting those shadows, realizing our models were incomplete because our observations were limited. The shadows were real. The observations were accurate, but they weren't complete. They were projections of a more complex reality we couldn't access with available instruments. Earth-space coupling, electromagnetic sensitivity to cosmic events, quantum precision detection of subtle field variations, AI-assisted pattern recognition in astronomical data. All of these capabilities came online or improved dramatically in the last few years. And now we're detecting things that don't fit existing models. Signals that challenge conventional understanding. Events that require either expanding our theories or accepting that coincidence can be extraordinarily precise. The comfortable interpretation is that we're just getting better at observing a universe that hasn't changed. The uncomfortable interpretation is that we're finally sensitive enough to detect interactions that have always existed but were invisible to crude instruments. And if those interactions are real, if Earth does respond to cosmic influences in measurable, potentially significant ways, then every interstellar object passing through our solar system isn't just a curiosity. It's a potential perturbation, a possible trigger, a probe testing systems we didn't know could be tested remotely. We're not just watching the sky anymore. We're measuring how the sky watches back. Let's review what we actually know. Not speculation, not interpretation, just verified facts that nobody seriously disputes. 3I Atlas is real. Confirmed interstellar object. Trajectory calculated. Closest approach documented. That's not controversial. The electromagnetic signal is real. Detected by multiple independent monitoring stations. 25 Hertz. Narrow band. Spectral purity inconsistent with standard natural. Electromagnetic phenomena. That's documented. The timing correlation is real. Signal occurred during the flyby window, specifically 3 hours and 20 minutes before closest approach. That's measured. Everything else is interpretation. And interpretation is where certainty dissolves into probability, where facts transition into models, where observations become theories that might be right or might be incomplete or might be completely wrong in ways we haven't imagined yet. Was this causation or correlation? Did 3I Atlas trigger the electromagnetic signal, or did two unrelated events happen to coincide with precision that seems unlikely but remains possible? Nobody knows. The mechanisms that could link an interstellar object to electromagnetic pulses at specific frequencies aren't established. They're hypothetical. They exist in research papers exploring edge cases and fringe possibilities, not in textbooks teaching consensus understanding. Was there intent? Was this deliberate action by designed instrumentation or natural interaction between objects we don't understand well enough to model accurately? Nobody knows. The signal characteristics are consistent with engineered systems, but consistency isn't proof. Nature can produce precision. It's rare, but rare isn't impossible. And absence of conventional explanation doesn't automatically mean presence of extraordinary explanation. Sometimes we just don't understand what we're seeing yet. Will there be consequences? Did that 25 Hertz pulse trigger something, prime something, set conditions that will manifest in observable effects? Nobody knows. If the Japan precedent means anything, if electromagnetic signatures at this frequency actually correlate with seismic stress, then maybe we should be monitoring fault lines more carefully. Maybe we should be watching for after effects. But correlation isn't causation, and pattern recognition in small sample sizes is how superstition gets built. These are the honest answers, the ones that don't make headlines, the ones that don't provide closure or certainty or satisfying narrative resolution. Science operates in uncertainty far more often than popular understanding suggests. Most research concludes with requires further study rather than definitively proven. Most phenomena get documented before they get explained, and most anomalies remain anomalous longer than anyone's comfortable with. But here's what has shifted: perspective, awareness, the recognition that Earth might be more responsive to external influences than our models account for. That interstellar objects aren't just passive rocks tumbling through space, but potentially active participants in electromagnetic interactions we're only beginning to detect. That our planet exists within a complex web of cosmic connections we've been too insensitive to measure until very recently. Maybe Earth isn't a passive observer after all. Maybe we're part of a dynamic system that responds to stimuli from interstellar space, from solar activity, from cosmic ray flux, from electromagnetic fields generated by objects passing through our neighborhood. Maybe sensitivity is the rule rather than the exception, and we've just been too technologically limited to notice until instruments improved enough to see what was always happening. That's not alarming. That's not prediction of disaster. That's not countdown to catastrophe. It's just recognition that our understanding is incomplete, that models built on observations from less sensitive instruments might be missing critical components, that Earth's relationship with the broader universe is more interactive, more coupled, more responsive than classical isolation suggests. The 3i Atlas signal is part of a larger pattern. Improved observation revealing unexpected phenomena. Enhanced sensitivity detecting subtle interactions. Better instruments showing that the universe is stranger, more connected, more responsive than theories constructed from cruder data suggested. We're not seeing new things. We're seeing old things clearly for the first time. And clarity reveals complexity we didn't know existed. Should we be concerned? Should this signal trigger alarm or investigation or institutional response beyond quiet monitoring and cautious analysis? That depends on what you think it represents. If it's natural phenomenon we don't understand yet, then concern is premature. If it's engineered interaction from designed instrumentation, then concern might be appropriate, but remains speculative without additional evidence. If it's correlation without causation, coincidence dressed up as pattern, then concern is unnecessary and potentially counterproductive. What we should be is attentive. Monitoring. Watching for repetition or escalation or additional data that clarifies rather than obscures. Science advances through accumulated observations, through pattern recognition across multiple events, through careful documentation of phenomena, whether or not immediate explanation exists. This signal is documented now. It's part of the record. It joins the Japan event, joins other electromagnetic anomalies, joins the growing catalog of observations that don't quite fit existing models. And if a third comparable event occurs, if another interstellar object produces similar electromagnetic signatures, if the pattern repeats with enough consistency to rule out coincidence, then interpretation shifts. Then models get revised. Then questions that seem speculative now become testable hypotheses. That's how science works. Slowly, carefully, building consensus through repetition, rather than jumping to conclusions from single observations. The problem is that waiting for consensus might mean waiting too long. Science demands rigor, demands reproducibility, demands evidence that satisfies peer review and withstands scrutiny. That process takes time, years sometimes, decades occasionally. And if these signals actually mean something, if they're precursors or warnings or measurements that correlate with real physical consequences, then the scientific method's careful deliberation becomes a liability. You can't retroactively prepare for events after they've occurred. You can't implement monitoring protocols after the pattern has already manifested completely. So, institutions face an impossible choice. Act on incomplete data and risk credibility loss, funding cuts, professional embarrassment when extraordinary claims prove ordinary after all. Or wait for certainty and risk missing the window where preparation might matter, where early warning could translate into meaningful response. Neither option is good. Both carry consequences. And the decision gets made quietly, behind closed doors, by people balancing scientific integrity against institutional survival. That's why public disclosure remains minimal. Why technical papers get published in specialized journals without mainstream media coverage. Why monitoring networks operate with increased sensitivity, but decreased transparency about what they're seeing. It's not necessarily conspiracy. It's institutional self-protection combined with genuine uncertainty about what incomplete data actually means. But there's another question underneath all of this. One that doesn't depend on whether the signal was artificial or natural, intentional or accidental. One that matters regardless of what 3i Atlas actually was or what it actually did. The question is this: if Earth is sensitive enough to respond to electromagnetic probing from interstellar objects. If our planet's geological and atmospheric systems can be triggered or influenced or measured remotely through the right frequencies applied at the right moments, what does that mean for everything else passing through our neighborhood? Not just interstellar visitors, solar storms, cosmic ray events, coronal mass ejections, magnetic field variations, all the electromagnetic phenomena that constantly wash over Earth from space. If we're responsive to those at levels we didn't previously measure, if coupling between cosmic conditions and terrestrial effects is stronger than classical models suggest, then we're more vulnerable than we thought, or more connected, or both. Vulnerability and connection are different framings of the same reality. A system that responds to external stimuli can be influenced by those stimuli. That's either a weakness or an integration, depending on whether you view Earth as isolated object or participating node in a larger electromagnetic network. Both perspectives might be partially correct. Earth has protective mechanisms: magnetosphere, atmosphere, geological stability maintained by processes operating over millions of years. But protection isn't immunity. Stability isn't invulnerability. The magnetosphere deflects most solar wind. Most, not all. The atmosphere absorbs most cosmic radiation. Most, not all. Geological processes operate on timescales that dwarf human civilization. Usually, not always. Earthquakes demonstrate that stable systems can transition to catastrophic failure in seconds when critical thresholds get exceeded. The question is whether those thresholds can be influenced externally, whether electromagnetic fields from space can nudge stressed systems closer to failure points, whether our planet responds to cosmic conditions in ways that matter for habitability and safety. We've assumed isolation for so long, assumed Earth's processes are primarily internal, driven by radioactive decay heating the core, by convection currents in the mantle, by tectonic forces building and releasing stress over geological time. External influences were considered minor. Solar radiation affects climate. Tidal forces from the moon affect oceans. But deep geological processes? Those were ours. Internal. Isolated from cosmic interference. That assumption might be wrong. Not completely wrong, but incomplete. Earth might be more integrated into its cosmic environment than classical geology acknowledges. More responsive to electromagnetic conditions in space. More sensitive to perturbations from passing objects, from solar activity, from the general electromagnetic noise of the galaxy. And if that's true, if Earth is a participating member of a larger system rather than an isolated ball of rock, then everything changes. Not catastrophically, not immediately, but conceptually. Our models need revision. Our monitoring needs expansion. Our understanding of what influences geological and atmospheric processes needs updating to account for coupling mechanisms we've been too insensitive to measure until recently. The signal that appeared on December 19th at 0240 UTC didn't provide answers. It provided questions. Better questions than we were asking before. More specific questions about how electromagnetic interactions work at planetary scales, about whether interstellar objects can influence Earth without physical contact, about what 25 Hertz means when it appears precisely timed to astronomical events. Was that signal a goodbye? A final measurement as 3i Atlas departed our neighborhood, gathering one last data point before returning to interstellar space? Or was it a warning? A demonstration that Earth responds to specific frequencies, that our systems can be probed remotely, that whoever or whatever sent that pulse now knows something about our planet's electromagnetic and geological vulnerabilities that we're only beginning to understand ourselves? Or maybe it was neither. Maybe it was just the universe being strange in ways we don't have framework for yet. Maybe natural physics produces phenomena that look designed when observed with instruments sensitive enough to see their precision. Maybe coincidence can be this exact, this well-timed, this consistent, with intentional action without actually requiring intention. We won't know until it happens. Again, or until it doesn't. Until enough time passes without repetition to confidently call this an isolated event, or until a second signal appears and pattern becomes undeniable. Science is waiting. Instruments are monitoring. Networks are watching. And somewhere in the space between observation and understanding, between documented fact and speculative interpretation, between what we measured and what it might mean, one question remains. The one nobody wants to ask directly, because asking implies accepting possibilities that challenge comfortable assumptions about Earth's place in the universe, and whether we're as isolated as we'd like to believe. Was that signal a goodbye, or a warning that something is already set in motion?